Okay, so oftentimes we got all sorts of different balls juggling in the air in our course. And that's because there's so much stuff to do, and I hate downtime stuff. So because that's the case, we often have to go backwards then and go over some stuff, right? So some other people have been working on other things for 20 minutes. Now I'm going to ask you to go backwards. The tough part about that then is stopping the stuff that you're working on. Right? So make sure that you put everything aside. Give me 10 minutes to do this and that little small sheet that we went over, and then you'll be right back at it, okay? All right, so look at so I took Zoe's numbers. I tried to email her thing to me so I could put the completed sheet up here as a PDF, but it didn't work. So I just put the blank one up here. I filled in her numbers. So let's take a look. Basically, at the back of the worksheet, everybody's answers should be very similar. Zoe's numbers we're going to deal with, right? But this way, you can check what you did. So basically, what we're here for is, again, our four main terms so far have been this idea of position, distance, displacement, and vectors. In both this thing and the question you started class with today are good examples of those four terms, right? So you've got your four positions. Zoe's positions were Clarence High School. I know Park City, Utah was one of them. What were the other two, Zoe? New York City and Yellowstone. And the order doesn't necessarily matter. It's the numbers that matter as we go back and look through the answers in the back. All right? So, the first thing I want to point out is there were some limitations to the Google stuff. If we wanted to get distance between any two places, there would have been a lot more clicking. I thought it was a little bit more difficult, so I kept this as a cumulative thing. But the fifth block here is just basically a repeat block. So if her total cumulative distance in that fourth block down was 6649, then her total distance was 6649. And I only did that because I wanted to make sure you had these two comparisons right next to each other in terms of distance traveled and displacement. Because if you go from Clarence High School to New York City to Park City, Utah, to Yellowstone, and back to Clarence, your displacement is always going to be zero, but you're traveling a particular distance. If I walk all around the room and then I end up right back at this spot, my displacement's going to be zero, but I'm going to walk a big distance. All right? And I wanted you to make sure that you have those two terms right next to each other. All right? So look at Jolie, can you read that first question for me?
What was the total distance traveled in your first trip, or was the total distance traveled in your first trip bigger than, smaller than, or equal to the total displacement for your first trip?
What'd you put?
I said the distance traveled was bigger than the total distance.
Yeah, how come? Justify your answer.
Because I started and finished at the same location, so the displacement was zero, but I traveled further.
Oh, perfect. All right. That distance is always going to be bigger because your displacement is zero if you start and end at the same spot. Same thing. The answer should be the same for question number 2, I think, correct? All right. Sometimes it's tough. Like you look at these 4 questions, the first one, they all kind of look the same. We got distance and displacement. We got first trip, second trip. Question 3, was the total distance traveled in your first trip bigger than, smaller than, or equal to the total distance traveled in your second trip? So everybody's answer here is going to be different. There's Zoe's total distance on the first trip. There's Zoe's total distance on the second trip. So her first trip's distance is smaller than her second trip's distance because 6649 is smaller than 11474. Again, I want to make sure that you have these terms, which is why we're asking these questions. But the total displacement, Richard, what do you have for question number 4?
The displacement of both trips is 0, so they're equal.
There we go. All right, now look at the structure of these questions. There's always an answer and some type of justification. It's very similar to your lab, right? The conclusion has to justify with your own numbers what happened with respect to that purpose. All right. What was the distance between your first destination and your first trip and your second destination? Really, all we're doing is subtracting these two numbers here, 4088 minus 3644 for Zoe is going to be, what's that, 444. Okay? And then do the same thing with the second destination between the second and third destination. So for Zoe down here, it's going to be 88, 98 minus 58, 7. We're just subtracting those things. So look at your justification, right? Show all work to receive full credit. So your justification, the answer could have just specifically have said, justify your answer for that last one. Math can justify your answer as long as the numbers are equatable and I can figure out where those numbers are. Oftentimes you have to have math and an explanation. Or, in the case of your small sheets, a diagram and an explanation worked out perfect. Before we get to that small sheet, Maddie or anybody else got any questions on this thing?
So for the first number 5,
Yep.
when it's asking about the first destination and the first trip and second destination, when you subtract the top two boxes, like the 43 and 3644.
Yes.
Okay.
Yes. So this is wrong.
But
And
then
then down here we're subtracting
Yeah.
58, 79, and 27, 29.
Wait, but then I thought you were doing what you did with the bottom one because you're doing the second and third one, and second and third destinations in the second box.
Yes. Yeah, it's
Okay.
tough with nothing written in here. You know what I mean? Like I didn't write the cities in here. So it's tough. So yeah, I would say what Maddie said. We're here minus here for this one, so that's my mistake. And then here minus this one for that one. Because your fourth destination is basically your current size. Okay? Thanks, man. Anything else here? All right, let's take a look here. Now listen, we're taking a look here, and then this is going to lead into a little mini 5-minute lesson here. All right, so however you got to justify that with respect to what you do with your notebook and stuff like that. Oftentimes, us going over stuff is not just us going over stuff. It is us getting into a lesson. So we'll use this to navigate our way into a lesson. Anything else down here, Frank? All right, we're doing any work, right? We're talking about some stuff here. And so my pictures are not as good as Zoe's or Maddie's or Andrew's, right? If there's my tree, that's my broccoli tree, not as nice as Zoe's. So I'll move my broccoli tree down. Move my broccoli tree down. All right, there's my tree. So, what happens here? Tony's standing at the tree, and he walks 400 meters. Eric, what is this thing right here? That is a vector. What does it represent? Okay, which is what do we call a term that has distance with a direction? Yeah, this represents a displacement of 400 meters, in this case, to the right. So he walks 400 meters in a straight line away. Tony then takes a break. When he starts up again, he walks 600 meters in a straight line. What's the key here? What's not mentioned about that second straight line? Yeah, what direction he's going in. So then he could walk 600 meters this way. And that gives us our maximum distance of 1,000 meters. Now, by the way, we did a great job. What I'm really doing right here is a little mini lesson on adding two vectors. It's called vector addition. What you just did, when you did that answer, is you added two vectors that were in the same direction. That's option number one. Option number two, which basically we all got, is that we go in the exact opposite direction. And what's my overall displacement in the opposite direction? Technically, this displacement is negative 200 meters, which means our minimum distance could be 200 meters. All right? So our answers here are 1,000 meters and 200 meters. Why? Because the extremes of what Tony could do is walk in the same direction for both of his paths and walk in the opposite direction. So now, this is vector addition. 400 plus 600. Here's the tricky part. This is also called vector addition. But mathematically, how do we handle this as a vector addition? Because they're in opposite directions, what do we do with the numbers? Subtract. So if we want to quote unquote add two vectors that are in the same direction, we simply add their numbers. If we quote unquote want to add two vectors that are in the opposite directions, we just subtract their numbers. Are these the only two things that Tony could have done? Now, Drew, what else could Tony have done?
You could have went like a certain angle from 400 meters away from the tree.
He could have went a certain angle. Let's go with the easiest angle for us to deal with. The easiest angle for us to deal with is if he went 400 meters this way, and then he went 600 meters that way. That's a 90-degree angle. How far away is Tony from the tree if he goes 400 meters this way, hangs a direct left on a 90-degree angle, and goes 600 up that way? Matt?
You have to like do a square plus b square plus c square.
It's exactly what you'd have to do. So it'd be, what, 1,600, 3,600 square root of 5,000, I think, maybe, that is. Right? Guess what this is called? Vector addition. How do you add two vectors that are at right angles to each other? You use the Pythagorean theorem. So how do we add two vectors that are in the same direction? You just add up the numbers. How do we add two vectors that are in the opposite direction? You just subtract the two numbers. How do we add two vectors that are at right angles to each other? Pythagorean theorem. Are those the only three situations? No, what else could happen, Nathan?
Could be that it's a non-right angle.
Could be on a not. It could be at any of the other angles. If I call this angle 0, and I call this 180, and I call this 90, we got 177 or 179 more angles to go. Any other angle makes it a little bit difficult. So if I take this as 400 meters, and I take 600 meters this way, this is a little bit more difficult. So we're not even going to go there yet. Possibility 1, possibility 2, possibility 3, which should be all mathematically relatively easy for everybody. Possibility 4 is going to cause us to use our old friends, sine, cosine, and tangent. We'll stop there for today with respect to this. Okay? So what was our little mini 5-minute lesson? The 4 different situations for adding vectors. Again, these could be displacement vectors, they could be force vectors, they could be velocity vectors, they could be acceleration vectors. We'll get into all of those things as the year progresses. All right? Last thing is I want to do before I let you go here is I want you to take a look at this. Okay? So this is somebody's, I don't even know that they're in this class or not. This is somebody's lab from the circumference equals pi times d. All right? Very common mistakes with respect to this lab, or with respect to all labs here, illustrated here, so I wanted to get out in front of this. So basically, what do we have for this lab? We had c equals pi times d. C divided by d is equal to pi. Basically, we had to show that the slope of the graph was at or near pi. And we do that in our conclusion. So let's take a look at this person's conclusion here. The theory that c equals 3.14d is correct. By calculating the slope based on the data, the slope ends up being very close to 3.14, which is also shown on the graph. Couple common mistakes. Okay? Number 1. This right here, this calculation of the slope is not the slope of this line. I think we know why this calculation is not the slope of that line. Jerome, give it a whirl.
Because he took 2 specific points and not like from the line of best fit.
These points could be like here and here, right? Like or she took an average of the data. We don't want an average of the data. If you're going to figure out the slope of the line of best fit, you got to take 2 points that are on the line of best fit and actually figure out their slope. That's number one. Reason number two, problem number two, is they never actually referred to their equation for their line of best fit. In other words, the slope ends up being very close, which is also shown on the graph. Does this person give me any indication that they actually know what the slope of their graph is? No. Other than randomly saying it's close to pi. And being right, because the slope is 3.24. Is that close to pi? Yes. But this sentence doesn't tell me they know that. This sentence tells me maybe they were listening in the cafeteria and heard somebody else working on this lab saying, all you got to do is write down that the slope is close to pi. Because believe me, there's plenty of people that take this course that don't understand that this is the slope. So instead, this sentence simply says, the slope is close to 3.14 because the slope of our graph is 3.24. Something wrong. You have to reference your specific numbers. So keep that in mind when you do this molding. Okay? All right, so what do we got for tomorrow? 3 things. Molding lab, post it on Schoology. 3 questions from your book, post it on Schoology. I think it was Drew asked, hey, we got to type those 3 questions. No, you can write them out and then just scan them into Schoology. And then this worksheet, right here with the answers right up here. Manny's already corrected my key. Listen, I make mistakes all the time. So don't feel bad to ask me about a key or anything like that. All right? You do not have to post this thing. You're going to bring this thing in with you tomorrow. Okay? Any questions? Sweet. So I got 20 minutes to work on all that stuff. I'll walk around and see if anybody needs any help. All right?